much. I want to welcome everybody to this session. We've had these NASA aeronautics sessions at Aviation since 2013. Every year we've tried to bring in a different bit of content, depending on what's kind of hot in the year and where we think we want to give an update. This year we felt it was time to do a Sustainable Flight National Partnership update. The really exciting thing about this is that we're beyond the plan and we're in implementation, executing at various phases in different projects, but it's more than a dream. Things are happening now. The video you saw was a real quick kind of 45-second flash through. You'll hear a little bit about different parts of what you saw in that video as we go through this with our various project representatives. Just one kind of orienting chart. When our boss, Bob Pierce, talks about NASA aeronautics, he talks in terms of four major transformations for aviation. Across the top, you see ultra-efficient airliners and future airspace and safety. Along the bottom, you see kind of new markets or re-emerging markets in form of high-speed travel or advanced air mobility, both of those. And they all have to connect up into that top right quadrant, the future airspace. Future airspace has to be able to successfully, safely, efficiently integrate all the different vehicles that want to fly in the airspace. Today, with the Sustainable Flight National Partnership and the airliners, we're focusing on the airliners and the part of the airspace that deals with the operations of the airspace. So I like to define sustainability because a lot of people, you can ask everybody in this room, you get a little bit different definition of sustainability. This ties back in large part to the United Nations definition about meeting the needs of the present and not taking away or affecting the needs of the future. But it's environment, but it's more than environment. It's the needs of society, it's economics, it's the needs of businesses, and you can find solutions in any one of these three circles. But if you forget the others, you're not going to really have a solution. And so you're looking for that target area in the middle there, that green spot in the middle, that it conveys how difficult a lot of what we try to do in the aviation community is. In the end, aviation is a safe, clean, quiet, efficient, economical, operable, and marketable enterprise. It has to be all those. In 2021, and this wasn't the first aviation climate action plan, but I think this aviation climate action plan that the FAA leads for the U.S. government and provides it to ICAO, the International Civil Aviation Organization, developed a really true kind of whole of government plan. And more than ever before, other agencies were very involved up front in kind of drafting this under FAA leadership and created this plan that was turned into ICAO and that we all use as a beacon. What you see here is the chart. There's various forms of these carbon wedge plots generated all over the world. This one is the one from the Climate Action Plan. It's centered on U.S. numbers, projections for U.S. numbers. But it's representative of what everybody else around the world's doing. So it relies on a number of basket of measures to get us towards net zero, including airline fleet renewal. That's extremely important. We know how hard that is. With supply chain issues we read about these days, but aircraft that are already certified or just about certified, they already have the NASA DNA in them. So that's up to the finances and businesses of airlines and providers to improve there. We focus then on the future in the blue area, the orange area, and help out in the green area with alternative energy. The blue area is where advanced aircraft, where we're trying to improve the efficiency of aircraft, which independent of what energy future we might have, we're always wanting to use less of it. Operational efficiency is the same kind of thing. making a more efficient system to save time, to save money, to save emissions. It's something that NASA takes a lead in. The green area, NASA plays more of a supportive role with the DOE, the FAA, USDA, and others in this country, leading the way on new energies from SAFs, various forms of SAF, to anything else beyond that. But the Climate Action Plan also talks very heavily about the SAF Grand Challenge in the U.S. that targets producing 3 billion gallons of fuel by 2030, sustainable aviation fuel, and 35 billion gallons by 2050. And I can tell you, if we didn't have the improvements we're working on for efficiency, that 35 billion number would be 50 billion. So efficiency is important. It's important, it's necessary, but it's not sufficient. So there's no silver bullet. Additionally, in the Climate Action Plan, it's not just about climate and emissions. It talks about noise, local air quality, other aspects. It has some policy work aspects that it talks about. It talks about non-CO2, including contrails, and we're kind of ramping up efforts to address that more fully now too. But my view of this is kind of the world knew carbon was number one, and everybody developed good plans for carbon, and they're working on them. And the chapters at the end of those documents that said, don't forget about non-CO2, we're now all working on non-CO2 roadmaps. Some are in place, but there's a lot of work going on in that now too. So, achieving net zero carbon, net zero greenhouse gas, and reducing contrails and other effects is important, while not forgetting about noise and local air quality and economics and all the other challenges that we have along the way. So within NASA, when we talk about the sustainable aviation strategy, we've gotten to where it's kind of two-pronged. Across the top, you see in green what we call the Sustainable Flight National Partnership, and you can trace it back more than a decade and even further back than that, but we kind of tend to think about it as around 2008, 2009, when we had the so-called N+3 advanced concept studies. That at that time were looking way out into the future, 2030 to 2035, and projecting beyond what was kind of the next product and getting out of the box to what was possible. We had several awards. There were other programs like ERA, Advanced Composites. We had demonstrator studies, a number of efforts. And over the course of time, with our partners in industry and academia and other government agencies, we kind of whittled down what were the most promising, beneficial, likely kind of technologies to focus on and take to the TRL-6 large-scale demonstration that's actually required. Too often, I know in my career, we take a lot of things to TRL-4, maybe 5, and you fall down the valley of death because of the expense of doing something big to really understand the integration, to really understand the benefits, to really learn what you need to learn. And it makes it very difficult for those in industry who make the decisions about products to have the confidence to do something that's a bit more radical than they would otherwise do. So that's where we are now, and what you'll see more today is, particularly in the technology area, is kind of where we've down selected and have cost-sharing partnerships with industry to kind of accelerate kind of the next generation, maybe skip a generation going beyond what would be a normal 15 to 20% kind of reduction, and trying to get 30% reduction in fuel, while being quieter, while not affecting local air quality worse, about all the other abilities to maintain everything. So in parallel to that, like we did in 2008, we're continually exploring, but there's kind of a concerted effort now with some university studies and another contract referred to as ACES that has not yet been announced who the awards are, but will be soon, that look out to the future, out towards 2040, 2050. And so while we're doing these large-scale demonstrations, we're exploring multiple options. I think in the green area, the Sustainable Flight National Partnership, you're in a world of kind of more or less drop-in fuels and targeting what we're trying to enter into service through industry in the 30s, because we can't wait. The longer we wait, the closer you get to 2050. 2050 is not moving anywhere. The planet's not waiting for us. It's not going to give us a pass. So we need to get new technologies in as quickly as we can. But while we're doing that, we're exploring with a wider aperture, what might be an alternative energy future, how would you get there, what are the different kind of technologies, and then maybe in the 30s we'll be doing demonstrations along those lines that lead to things that can go into service in the 40s. So that's kind of how we bracket this. In the Sustainable Flight National Partnership, as I said earlier, we're trying to accelerate us towards net zero by doing things as quickly as we can. It takes time. It takes time, but we're doing them as quickly as we can, trying to get technologies demonstrated in the 2020s by the end of the decade, so informed decisions can be made, in industry. And also looking at non-CO2 impacts, so that's where some of the contrails work comes in that cuts across a number of the activities. But we have activities on advanced engines and emissions, advanced airframes, manufacturing rate, improved trajectory, more efficient operation of the aircraft, and everything kind of pointing towards being able to use the 100% sustainable aviation fuels. So with that, we have lined up a list of panelists here. We had a few last-minute changes due to a variety of reasons, but we have, so Gowdy's not here, but Joe Connolly's here from the Electrified Powertrain Flight Demonstrator Project. He's the Technology Integration Manager. Then we'll have Tony Nerone, the Project Manager of the High-Tech Project, Rick Young, who's our High-Rate Composites Project Manager, Brent Cobley, who's the Subsonic Flight Demonstrator, or X66. I'm really happy we brought props from the exhibit hall, so you can see X66 over there, and there's some smaller models of the electrified powertrain demonstrator aircraft here. Swati's representing the air traffic area, and Dale is standing in for Eric Hendricks to talk about the model-based systems analysis and engineering, and we might be able to pull out of Dale a few things that are beyond SFNP as well, too, along the way. So with that, I want to turn it over to Joe, not Gowdy, Joe. So.
Thanks, Rich. All right, well, thanks everyone for joining us this afternoon. I apologize that you don't get our project manager, Gowdy. She's feeling a little bit under the weather today, but hopefully I'll do her justice as we talk a little bit about the Electrified Powertrain Flight Demonstration Project. So NASA's been working in the electrified aircraft propulsion area for well over a decade now. And when we were first getting started in this area, we wanted to take a look at a couple of key areas that we thought were going to be some of the key barriers that were going to cause us trouble when we're trying to get these new technologies into aircrafts for entry into service in the 2030s. So a number of the key tech risks that we pointed out were the high voltage operation at altitude, thermal management, the battery system shortfalls for performance, and we went about trying to address some of those technologies by developing new capabilities at NASA. One of the key ones that we worked to develop was the NASA Electric Aircraft Testbed, a new test facility that allows us to get to the megawatt class scale and have an altitude chamber to begin to understand how these systems are going to operate at high voltage in an high altitude condition, the relevant environment that we want to actually test in. Another key area that we were taking a look at is battery system performance shortfall. So before the EPFD project went out to some of the larger contracts that we currently have, some of the things that we wanted to do was to address some of these barrier risks, and the battery is one of those key things. So we were able to have a whole group of industry come out and work with us and try to address some of the key barriers that we had. So we had a number of industry companies that were looking at battery systems and doing studies to reduce the risk. So then when we went out for our larger flight demonstration contracts, we would have greater confidence in the success of that work. We had a great discussion of all of the industry partners that we've been working with throughout the EPFD project. Yesterday in an afternoon panel sessions, we got to hear from a number of the risk reduction contract award winners that help address some of these issues. Some of the other key issues that we're working to address in terms of risk that we saw were the propulsion system integration, the powertrain system integration, and the aircraft system integration. And this is where Rich was pointing out, we've done concept studies, we've done component work, and that has been great and very successful. But the exciting part where we're at right now is we're actually starting to get to real demonstrations, the real system getting out there, fielding it, and whenever we're doing those kind of larger scale demonstrations, it's really the integration issues between all of the different subsystems that become the real barriers for entry into service. And that's what we're trying to tackle here with the flight demonstrations for EPFD. So a little bit about the general scope. Our main goal here is really to enable megawatt class electrical powertrains for future aircraft. We're looking to do this for both the single aisle regional markets, and we're trying to target an entry into service for these technologies in the mid-2030s. One of the things that we've been doing on the EPFD project is really have an industry-led initiative. So we have two contracts that we'll talk a little bit about, one with GE and one with Magniex. And industry is really doing the technology development and leading the way under the project here. Another key part of it is also making sure that not only are we doing the research and the technology development, but we really want to see these technologies be fielded and entered into service. So a key part of it was having the companies identify vision systems that they could use in the future, and then also identifying all of the regulatory gaps that need to be addressed for entry into service for the electrified powertrain system. So with that, we're really trying to get the electrified aircraft propulsion systems into the next generation of aircraft. If you're attended any of the EAT sessions earlier in the week, Christine Andrews of GE gave a wonderful talk about some of the initiatives that GE is undertaking in terms of the electrification process, and in part with NASA on a couple of different projects. But I'll just talk a little bit about what GE is doing right now in terms of our work together on the electrified powertrain flight demonstration. So GE's looking to modify a Saab 340B aircraft, a regional turboprop, and to modify the CT7 engines for electrification. One of the key things that they're doing for GE's technology development is that they're hybridizing the aircraft at the propulsion system. So you can go onto YouTube and search GE, and you can see some of the videos that they have in terms of how they're looking to integrate the electric machines into the actual CT7, so that you would have a hybrid system right at the propulsion system level, where some of the power is coming from the fueled CT7, and also some of the power is coming from an electric machine. To actually do the flight demonstration, GE partnered with Boeing. They're helping with the aircraft integration systems, and we're looking to do our demonstration in the mid-2020s. Where this all goes and where GE wants to take some of the technology that we're developing under the EPFD project is integration into their RISE program. So here we're looking at developing the fundamental technologies on the electric side to understand how electric machines can integrate with turbo machinery, and then integrate that together and contribute to the electrical powertrain needs and the technology development that would support a future RISE system. So we're really excited about the work that GE is doing, and are excited that we're getting closer to really seeing these systems actually fielded and demonstrated. Another company that we're working with is Magniex. They're a little bit smaller on the startup size, where GE has a legacy of being able to field turbofan engines and being a leader in electric propulsion and electric machine development, magniX has done a whole series of different flight demonstrations and has been a leader in terms of getting their technology flight tested early so they understand a lot of these integration issues. On the magniX side, we're looking at modifying a de Havilland-7, and we're going to integrate it with the electric propulsion units that magniX are developing. These are their Magni 650, so in the 650, 700 kilowatt range for their electric machines. One of the things that we're taking a look at is with this aircraft is that we'll be able to have two gas-powered propulsion systems, and then also modify the outboard engines to integrate the Magni 650 so that we have electric propulsion on the outboard propulsion systems for the Dash 7. One of the key things that has been really exciting recently with magniX is they recently completed some of their initial testing of their EPU system at the NASA NEAT facility. So we have a couple of news articles if anyone's interested in learning more on the successful testing that we've been able to do on their electric propulsion unit at simulated altitude for the demonstrator upcoming. One of the other key things with the magniX system is that the hybridization's at a little bit of a different level. When we were talking about GE, the hybridization is really at the propulsion system. With magniX's concept, the hybridization is really at the aircraft system level. The electric powertrain is really isolated from the gas turbines, so we're able to have a little bit of a simpler approach, but the hybridization still provides the overall benefit. And at the regional level for the vision vehicle that magniX is looking at, we're really potentially getting some really significant benefits for the market where they want to introduce their hybrid aircraft. So they're looking at fuel savings on the order of 40% for 200 nautical mile missions. So something that could really provide a big benefit for the overall community. Where NASA and where EPFD is sort of fitting into the Sustainable Flight National Partnership is we're trying to develop and bring this technology to a place where we can actually see it integrated into the next generation of aircraft. And we're also going to be collecting data from both of these demonstrators and sharing it across the SFNP network so that we're able to develop new models, refine our technologies, and be able to do the future concept studies that we need to accomplish to get to that net zero by 2050 goal. So we have a number of different challenges to get to net zero by 2050. It's going to be a really hard thing to do. But with electrification, I think that the electrical powertrain can fit into a number of different aircraft concepts where we can play a significant role. And I think with having such a challenging goal of getting to net zero by 2050, we're probably going to need a broad spectrum of team, just like we have up here on stage. We won't be able to get there without a whole suite of technologies to get us to where we want to be, and it's exciting to be a part of that and be happy to take questions on the electrification that NASA is doing for our flight demonstration projects. So with that, I'd be happy to welcome Tony Nerone.
All right, thanks, Joe. All right, hello everyone. I'm Tony Nerone. I'm the project manager for HITEC, which is the Hybrid Thermally Efficient Core Project. So the goals of HITEC we're basically the engine project of SFNP. We're focused on the turbofan engine technologies for the next generation single aisle. And so we're focused on accelerating those technologies for turbofan engines in compact core. We're trying to shrink the core of a single aisle engine to improve the fuel efficiency, emissions, and ultimately help meet the Sustainable Flight National Partnership goals. The technologies we're focusing on are related to durability, performance, efficiency, also hybridization and sustainability for that next generation aircraft. So when we formulated the project, we tried to find some key objectives to have related to that. And overall, when we develop the small core for next gen, we want to have 5 to 10% fuel burn reduction just from shrinking the core of the engine. So that overall 25 to 30% you see for SFNP, 5 to 10% of that will come just from shrinking the engine core. And we talk about shrinking the engine core. It was said the other day, I like the way GE phrases it when they talk about having a single aisle fan being powered by a business jet size core, and that's pretty accurate in terms of size for what we want to do for shrinking that core. We also want to achieve 50% or 20% power extraction, which is 4 times roughly what we have today. And that's related to the hybridization piece when we say hybrid thermally efficient core. We want to bring hybrid electric technology also into these next gen engines. And here we're trying to prove we can extract a lot more electric power off of engines than we can today. And it's with both spools, and I'll get into that a little bit later. And we also, as we go to the smaller cores and smaller combustor technologies, we want these engines to be able to be fully compatible with sustainable aviation fuel. So with the smaller core, we want all of them to be able to run on greater than 80% by ideally 100% SAF without any change in performance. So you can run them on Jet A or SAF without any change in the way they perform. Now, when we talk single aisle, we looked at primarily thrust class of 25 to 35,000 pounds of thrust. That's kind of what you see today in a 737 MAX or A320neo. That's kind of the target we're looking at. And that did omit some companies we could work with because we wanted to have someone that had a single aisle product and was going to have a single aisle product in the future. And with that, we've developed some metrics for our project called key performance parameters. I don't show them all here. We have a list of them. Some are related to durability and SAF and all those things. But these are 3 key ones when we're talking about small core. We want to end up, when we're done, having an engine bypass ratio of greater than 15, a overall pressure ratio of greater than 50, and a high pressure compressor exit corrected flow of less than 3 pounds per second. And so you look at that, you say, what does that mean? Why is that important? So let's get into that. So this is helping define what small core is. So this figure is from a paper, an AIAA paper from 2015. And I'll try to set it up as best I can. If you're familiar with, NASA had the M+1, 2, and 3 goals that were put out about 2008 or so, 16 years ago. And this paper was about 9 years ago. The shaded areas of blue and green with the dots, those were current engines in production in 2015. So ignore the red dot and the red circles for a second. And then you see the M+1 goals and the M+3 goals. And M+3 was meant to be 3 generations from where we were in 2008. So it would have been the 2030s. And at the time, you could see all the engines were well below that. And M+1 was a feasible goal within the first 10 years or so. Then we move on to high tech. We're starting to put together the project. Where were we in 2020? So you see the 2 dots that are circled there that we added to this figure. That's the high tech baseline. So one of those is the CFM LEAP, and one of those is the Pratt & Whitney GTF. Those were the newest engines that had come out 5 years after this figure was created. And you can see they're better. They're incremental improvement, but there's not a huge improvement. So when I talked about those metrics on the previous page, you see the x-axis is the core size in pounds per second, and the vertical axis is the overall pressure ratio. So those best-in-class engines that are flying today are right around 4.5 pounds per second in terms of the core size, and their overall pressure ratio is high 30s, low 40s, around there. So then we talk about the goals I just showed you in the previous chart of 15 for bypass ratio, overall pressure ratio of 50, and a core of 3 or less. That's the big red dot that we're going to. And the point of that is to show this is not an incremental improvement. This is not evolutionary like we've had in the past. This is going to be a big jump in technology. And in fact, when we're done with this and these engines are in production in the 2030s, we're getting really close to those aggressive M+3 goals that were set up about 16 years ago. So if this actually happens, we actually are able to execute all these technologies, we're going to make a huge improvement in engine technology and actually get close to those aggressive goals that were put forth a long time ago. So how are we doing this? We've divided the project into 2 phases. And so the first phase, we were targeting individual technology development and targeting a minimum, when we're done with phase 1, of technical readiness level, TRL4. Some will get to TRL5. We've made awards to both Pratt & Whitney and GE Aerospace. And these are the technologies, there's at least one contract in all these different areas. We chose these technologies because we wanted to be able to help industry accelerate these technologies. So these are all cost share contracts where there's minimum 50-50 from each partner in this. And we just didn't want to put funding behind it. We also wanted to have NASA subject matter experts and facilities help accelerate these technologies. So we looked for ones where we were able to do that, and these are all the ones that fit in that category. So I'll go through them real quick. Turbofan power extraction, I mentioned that. That's basically hybrid electric. We say dual spool power extraction. We're trying to pull power off and put power back on both spools of the engine, the high pressure turbine and the low pressure turbine. That gives us that higher level of 20% extraction and the ability to put electric power back on the motor to help assist and help with fuel efficiency. We have combustor technologies developing these small core combustors that are also fully compatible with SAF. And we have a lot of materials work too. We have enhanced combustor materials. So those are ceramic matrix composites to increase the durability in the combustor section. And also CMCs with environmental barrier coatings in the high pressure turbine section. If we're going to go to smaller core, we're going to have higher temperatures. And one of the enabling technologies is to have high temperature materials that enable that higher temperature operation. And then in the aerodynamic side, again, we're shrinking this core. So you have a core that's going to be 30% smaller, but it has to produce the same amount of power. And in that regard, you have to get a lot more work out of all the blades and the turbine and the compressor. If you're going to go to these higher overall pressure ratios, the compressor has to go from 40 to 50 pressure ratio. So a lot of different aerodynamic tricks, advanced airfoils, casing treatments, things like that we've been working on to try to enable that small core operation and get the same amount of power out of a smaller one. I'm happy to say that a lot of this work did get done at NASA Glenn Research Center in Cleveland. We did materials testing with these high temperature materials. We've done turbine and compressor components. We've done power extraction, hybrid electric work. So we did achieve that goal in phase one of actually helping to accelerate these technologies using our researchers and engineers and our facilities at the Glenn Research Center. So when we get to the end of phase one, how are we going to measure our performance? We say we have all those key performance parameters, and those are the ones we're going to use when we get to the end, and we have the vision system, and we have the core developed. But when we're done with phase one, how do we measure our progress? So this is just a systems analysis projection with all the technologies we have. We did this for both the LEAP and the GTF, but this is an example using the LEAP. Or what if we took the technologies when we know how they're performing at TRL4 at the end of phase one and retrofitted them into a current engine? What would be the effect? And so this is also assuming all of our phase one contracts end fully successful. So at the end, we'll end up putting the final results in here and rerunning all the models to see what we ended up with. But if everything works out well, you can see it's a pretty substantial improvement. We actually get a 5.2% fuel burn reduction using these technologies in a current engine. The bypass ratio of a LEAP jumps from 8.6 to 10.8, and the core size drops from about 4.2 all the way to 3.25. So that's pretty substantial progress just doing individual component tests in phase one and getting to TRL4. So we're hoping when we're done, we'll have numbers pretty close to this. Now I'll talk about phase two. We have already awarded phase two, even though we're not quite finished with phase one. And we did select GE Aerospace for our second phase. We made that selection in December, and the contract just started this last February, so within the last few months. Again, it's a cost share contract with at least 50% share in GE side. We're putting $68 million in. The point of phase two is to then integrate all these technologies together. We're going to design, build, and test an engine core. It won't have the fan on the front or the low pressure turbine, but we're going to build and design this advanced small core and test it to see if we meet all of those metrics that we set forth at the beginning of the project. And the point here is to integrate all those some phase one technologies into phase two and see how they all work together in an integrated core. So this is phase two, and these are the technologies in phase two, which are very similar to the phase one technologies because we kind of kept it to the same trade space. So when we're done with this, the core demonstration will hopefully have demonstrated hybrid electric, high pressure compressor, the combustor again, enhanced materials, and high pressure turbine technologies, all in an integrated fashion, in which we hopefully will meet all those key performance parameters at full success and set up the next generation of engine technology. So we have a core that will be the basis of future single-aisle flight. This will help meet the SFNP goals and ultimately the U.S. Climate Aviation Action Plan. So we're hoping to do this by 2028, the end of 2028. We're hoping in 4.5 years this test will be complete and we'll have achieved all those goals. Okay, well with that I'm going to turn it over to Rick Young to talk about the HiCamp project. There you go, Rick.
Thank you. Good afternoon. My name is Rick Young. Let me see if I can advance. Yeah, I'm the project manager for NASA's high-rate composite aircraft manufacturing project, and I'm going to give you a brief introduction to the project this afternoon. I'm going to start off with just introducing the topic of why composites and why high-rate manufacturing in a sustainability session. It was mentioned in the previous talks that our next generation aircraft are anticipated to be 30% more fuel efficient. And again, the objective there is to attack really the highest, largest aspect of carbon dioxide emissions for aviation. And composite airframe can have basically a big contributor to fuel efficiency. It's anticipated that a composite structure in the airframe can be about 25% lighter than a metallic airframe. And it's been projected for the single-aisle airplane that a largely composite structure could yield a 5 to 8% fuel burn benefit. In addition to that, composite structures can tend to enable low-drag configurations like the truss brace wing configuration. In general, reducing fuel burn reduces operating cost, but also composites are noted as also reducing maintenance costs. So again, attractive for sustainable operations. And in relation to cost, though, I want to mention that there's an additional desire in composite manufacturing to reduce the cost of composites production by 50% relative to today's composites fabrication in order to be cost competitive. Now, the other aspect is high-rate production. It was mentioned in Rich's charts that we're showing fleet growth in the next 2 decades. It's been anticipated that over 33,000 single-aisle airplane will be produced in the next 20 years. This is largely replacing our aging fleet with more efficient models, so replacing 70% of the current fleet, but also doubling the fleet size because of the increased demand in seat miles. This represents a $7 to $8 trillion market being estimated, and there's a large desire in this country to capture that manufacturing here in the U.S. So based upon that, Boeing and Airbus have projected in their future fleet projections a desire to be able to produce a single-aisle aircraft at the rate of 80 to 100 airplanes per month. I want to compare that to our historic production rates for our single-aisle class aircraft that have been constructed out of metals. We've been producing those at about 60 airplanes per month, so that would be about a 30% increase to get to 80. But our history in producing composite structures on aircraft like the 787 and the A350 or the new A220 haven't exceeded more than about 14 airplanes per month. So to be able to produce 80 per month would represent about a 6-fold increase in production rate. Now, one of the things is, so as we move into this project that was formulated in 2021, it was centered on developing a high-rate composite manufacturing capability for large aircraft structures to help meet aircraft demand and to enable improved fuel efficiency on that next single-aisle airplane. So the goal of the project is to develop manufacturing technologies that are applicable to large composite structure that are able to produce this aircraft at 80 aircraft per month with reduced cost and without increasing the weight. We still want to take advantage of lightweight composite structures and still produce them at high rate. And this is compared to current technology. And for development and transition to those technologies for an aircraft application on the next single-aisle airplane in the early 2030s. So the objectives are focused on developing high-rate manufacturing techniques, but also developing model-based engineering tools necessary to be able to apply those manufacturing techniques on the next airplane, which is, again, in short term. Our approach is to basically start with a baseline production system baseline that was defined based upon our 777 wing production and our Boeing 787 production system. And then look at competing manufacturing approaches using a next-gen thermoset or resin infusion composites or thermoplastic composites. And using a system-level assessment, assess the production performance and the component performance using these advanced manufacturing techniques. And then develop and demonstrate that capability at full scale by the end of the project, currently FY28. We're executing the project through a public-private partnership. We currently have NASA, the FAA, and a total of 20 members who are working together to develop this technology. It includes original equipment operators, first-tier suppliers, machine makers, material suppliers, and universities, working together across the supply chain to develop and advance these technologies. We're working under a public-private partnership with 50-50 cost share, forming cooperative research teams that have more than a dozen members working together to share in the cost and the results that are developed by those teams. As we go forward, in order to assess the performance of a high-rate manufacturing technique, which is relatively sort of an arbitrary measure, it was necessary for us to develop sort of a system approach to evaluating the efficiency of a production system. So we started first by developing a vision system. We selected a generic narrow-body aircraft configuration and typical aircraft construction for fuselage and wing structure, and designed geometries that could then be challenging our teams to fabricate those at high rate. We then asked them to develop a manufacturing model of their future system that would say, if given your production approach, define the component construction, which would define the weight of the structure, and then define the factory that would basically build those parts. It starts with defining the activity that would have to occur at each station and the equipment necessary, which would define the cost and duration at each station. But then you could assemble those stations into a factory flow and do a sort of a discrete simulation of a factory model in order to determine the size of the factory, the number of lines that would need to be produced to produce a certain number of ship sets per month. And by doing this, you could estimate the weight and the production rate, the non-recurring costs, the recurring cost, and the factory area of this future factory. We then developed a system for the baseline configuration based upon current manufacturing technology that's in play, and then compared it to advanced production systems, competing next-gen thermosets, these resin-infused composites, and a thermoplastic composites approach. We had a goal of a modest weight reduction, just enabling the use of composites on a single-aisle airplane, and also achieving an 80 aircraft per month production rate, and then between the recurring and non-recurring cost, basically getting a net 50% reduction in the per unit cost. We've been executing the project in parallel with these other projects that are being presented. We're currently in the middle of the project and approaching a decision point for down selection of technologies to go into the second phase of the project. I'll describe briefly what we've done in the first phase, which is really technology development of competing manufacturing approaches. And then I'll tell you where we're headed in the second phase of the project, where we'll be demonstrating those technologies on large-scale components, doing multiple builds for wing and fuselage components. So in the first phase of the project, executed from FY22 to 24, we've been doing process development and material evaluations and working from the small scale up to sort of medium scale component builds. We've been making up to 5-foot element sections and 4-foot by 8-foot panel in order to evaluate the performance of these different competing systems. Again, we're not just trying to go faster, we're trying to develop technologies that can be processed faster. So it's a bit of a take a couple steps back, formulate new approaches, and then try to implement those into producing something of high quality. We're taking 3 different integrated product teams are pursuing 3 different approaches. The first one is in a next-gen thermosets, which is really evolution of the current state of the art. Greater automation, introduction of more in situ inspection, and then also going to a faster cure time in the autoclave. Again, it's putting down pre-preg material that's fiber reinforced, carbon fiber that's been pre-impregnated with a thermoset resin, and then cured into a solid laminate in like an 8-hour autoclave cure cycle. The second approach that's competing that is a resin-infused composites, where we're putting down multiple layers of dry fiber at a time for faster laydown rate, but then we're putting that fiber into a closed mold and injecting resin, and then curing that out. And we're using a new rapid cure resin that can be cured at a single temperature, so there's no ramp up or cool down. We load the tool hot, we inject it, it cures out, and then we take the part out. By doing this, we can drastically reduce the time on tool and reduce the number of tools necessary to produce those parts. The third approach is using thermoplastic composites, where we're taking advantage of the characteristic of a thermoplastic where the fiber is already surrounded by, encased in a plastic that can then be melted and reshaped and then consolidated and then melted again and reshaped. And by doing this, you can start with sheets of carbon fiber reinforced plastic that can be assembled into complex configurations, can be then heated and put into stamp forming presses, and then ultimately can use reheating in order to weld the components together. So this is a way of basically a different approach to assembling the structures at a rapid pace and a different approach to assembling them in the final components. Goal of doing this is basically getting parts fabricated faster, through the equipment faster, so that you can have less equipment and ultimately produce aircraft at a lower cost. As we go into the phase 2 of the project, we'll be selecting technologies now to go up to larger scale fabrications. We're taking an approach where we'll be developing large scale demonstration for wing box construction and for a fuselage section. We're selecting technologies that will be used to produce multiple subcomponent replicates that then will go through demonstration of assembly of those, which is the second part of the factory. We'll be doing multiple ship sets, and we've picked a size that's a little bit smaller so that we can do more replicates and demonstrate fabrication of parts at large scale, at rate, and with multiple replicates in order to demonstrate quality. One of the things that we've learned in doing this, though, is when we first were evaluating approaches to this, we thought we would have a leading manufacturing approach that would emerge that would be used to fabricate the entire part. What we've concluded, though, a couple of things. As we are competing in next-gen thermosets versus resin infusion and thermoplastics, some of the approaches are lower risk, but yet yield lower benefit. And at this point in time, based upon our smaller scale assessments, we're not ready to make a determination of which one is the best approach that has a high likelihood of going to the largest scale. So we're going to be constructing these using a sort of a hybrid approach. We'll be fabricating certain parts of these components using one manufacturing technique, which may be a lower risk, and we'll be fabricating other parts using a more high-risk approach, and be able to show how each of those now compare at a larger scale. For example, the upper wing skin of the wing being made using one technique, and the lower skin panel being made a second technique. By doing that, we'll be able to evaluate the ability to produce larger components. We'll also be able to do assembly tasks, though, even though the parts are made using different techniques, in order to accelerate our assembly processes. And by doing so, we'll be able to make a recommendation at the end of the project of the best approaches toward fabricating the next single-aisle airplane. Okay, with that, I'll close, and I'll just point out at the bottom of my chart, I do have a link to our project website so that you can track our progress as we execute the project. Thank you. And with that, I'll turn it over to Brent Cobley, who's the project manager for the Sustainable Flight Demonstrator.
Oh, that's a good idea.
I think I will start on this side of the stage. Just everybody who has a kinky neck can look this way for a little bit, and I like to stand next to the model. It makes me look good. So a year ago, I was at Aviation in San Diego, and looking forward to informing everybody about the progress we had made since we had recently awarded the airplane contract, or the agreement with Boeing. And also to announce that we had been honored with a designation from the DoD to be X-66. And the X-66 was the first X-plane designation given for a vehicle that was focused on sustainability. So I think that was a big benefit we wanted to share with everybody. Unfortunately, the night prior, my wife called to tell me that she had blessed me with COVID, and so I wasn't able to actually get on stage. I called the person organizing the event, who's Barb Esker, sitting right over here, and she was very sympathetic, saying something to the effect of, "You're not getting on my stage with COVID." So you all got to meet my deputy, and she did a fantastic job getting you up to speed on what the aircraft is all about. So I titled the talk, "What have you done for me lately?" I'm going to give you just a little bit of, the first year for those of you that don't know much about the airplane and the project, and then focus most of our time is like, what have we been doing for the last year? How much progress have we made? You can see the aircraft is a transonic truss brace wing, very long aspect ratio to get better performance, lower drag, and less impact on the environment, of course, stabilized by these diagonal struts for structural purposes. So that is the key part of what we're trying to test, but it's really a lot more things that we'll cover as we go through the brief today. The other thing it enables, I like to point out, because I'm not going to spend any more time on it later, is when you go to a high-wing airplane for a single-aisle class, it gives you the opportunity to kind of expand the propulsion system you put on the airplane. Today's systems are so close to the ground, you really can't go to higher bypass ratio. So it really opens up the design space to also include additional propulsion system benefits in addition to a lot of the other structural benefits and stuff that were covered. So I'm going to just, with one slide, go through kind of where we were the first year leading up to last year's aviation conference. So we put out we put out a call for proposals prior, a little bit of over a year prior, right actually around the aviation the previous year. We had proposals due in September. We went through a process to evaluate those against our criteria, and we actually received more than we expected. Took a little bit extra time, but we got to the point of doing the award out in January. You can see the NASA administrator was very excited to announce that, and what we awarded was not a contract. And I think it's a key part of what this project's all about to kind of describe what we did do. We used a funded Space Act agreement, which has been used in the government for other purposes. But not much at NASA other than in the space world. Things like commercial crew use a funded Space Act agreement. And the reason is the funded Space Act agreement is really set up to not benefit NASA. It's set to benefit something else, and in this case, industry and really the public. And so it has to have alignment with our goals, but our goal is to try to make something happen that we want to make happen, but really benefit for others. In this case, the environmental benefits is a key part, but also sort of balance of trade and manufacturing jobs and so forth. So a funded Space Act agreement is unique in that it's basically industry-led. You can partner with the government can participate, but the government, we did not write requirements for this project. We did not tell them what kind of configuration to build or how to do it or how to run the project. And that's really a key thing. Our goal was, how do we make sure that industry takes a technology like a new configuration through the valley of death and get it to a TRL level so they're ready to make a commitment to taking that actually to market. And the way to do that is to let them do what they think they need to do to get there. To use their own requirements, to use their own processes. And so we set out these goals of what we were trying to achieve. And in the proposal process, we said, you tell us the right configuration that you think is marketable. You tell us then what questions you need answered before you're ready to actually make a commitment to turning that into an aircraft and putting it into production. And so basically that's what the proposals were and how we evaluated them. So the government is participating, NASA. We're providing some funding, but the vast majority of the funding is coming from Boeing, who won the award. They're putting in an estimated $725 million to NASA's $425 million. But we're also providing support, technical support, people on the team and facilities and doing various types of activities in partnership with them. So we're helping, but it's really, like I said, an industry-led activity. It is cost shared, as I mentioned. The other unique thing about it is the $425 million is the total amount that we're going to give over the life cycle of the project. We pay the partner at intervals as certain milestones are achieved, like design reviews and other things like that. We don't, if there's an overrun, a delay, we don't pay for that. So the risk is theirs because the benefit is theirs, and then because they're bringing their own money to the table. In sort of what the government gets out of, or what the industry gets out of that, is they get a lot of protection for the IP under a funded Space Act agreement. And that makes sense. They're putting a huge amount of money. We shouldn't be going around publishing everything they're doing. So it is a very unique way of running a project. We got a lot of stuff done later in the year. We did kickoff. The blue things are basically some of the payment milestones. So we walked through how we're going to do airworthiness. NASA is going to provide the airworthiness certificate. That's one of the only requirements we had in the whole activity. And then, as I mentioned, we briefed everybody last year at Aviation. Of course, in parallel with that, all that activity was just tons of technical work, design work, trade studies, ongoing. The vehicle had already been designed and was pretty far along, but obviously not ready for manufacturing and so forth yet. So what's happened since the last aviation conference is, number one, Boeing got a couple of airplanes up and flying that were in mothballed, former Delta Airlines aircraft. And so these are going to be the donor airplanes that they're going to modify into the configuration you see, the X66. And so they actually brought 2 airplanes up and ferried them from their, where they were stored over to their Palmdale facility where they're going to do all the modifications into the X66 configuration. And then we went through a concept design review activity in September, which is a multi-day, very complex review. It was a review for Boeing and for NASA to participate in. It was also a payment milestone. And after the airplanes got in Palmdale, this little video here of them starting to do modifications. We're a long way from finishing the design and fabricating the wings, but they've already got the engines off. They did a lot of scanning of the airplane to make sure they understood. A lot of these older airplanes are kind of manufactured with some wider tolerances. They want to make sure they understood that and they could design to that exact shape. We did a system requirements review last December. Again, multi-day, very complex, deep dive into the requirements and how everything fits together. And then we got into wind tunnel testing. Again, in parallel, lots of other things going on, which some of which I'll go through. We just finished the first round of testing in the 12-foot low-speed tunnel at NASA Langley. This is a very low-cost tunnel, used 3D printed models. In my mind, we weren't going to learn a lot from that, and I was very wrong. We learned a lot from this test. It was also a very good way to kind of help plan for the later tests, which are actually ongoing right now, which are much more expensive tests, and it helped us refine the test matrices. But we did look at things like deep stall. When you have a T-tail airplane like this, you worry about deep stall. That turned out to be not a concern, luckily. And so we completed that. We're going to do a little bit more testing in August in that tunnel. But really what's going on right now, and this is actually running 2 shifts a day every day right now, is this 11-foot test out at the Ames. This is a very high-quality tunnel, very expensive to operate, high speeds all the way up to cruise conditions for the airplane. We started off with a half-span model, which you can see in the far right photo there. And the goal is to build as big a model as possible that you could fit in the tunnel. And by building half the airplane, you can get a lot more data, but you can't get sort of side slip data and things like that. So the goal with that is to really understand some of the basic aerodynamics, but especially the loads on the vehicle. That's used to validate a lot of the predictions that as we're going through the design cycles for the wing. We really want to make sure we get the skin thickness, all the different material thicknesses proper and dialed in. You don't want to have a lot of excess margin because that's weight and you lose efficiency that way. So that's a very high-end test. It's going to run for a couple of months, as I said, in progress right now. We'll come back into that same tunnel with a full span model, but half the size, starting in late October, and do another couple months of testing. Sort of in parallel with sort of all of that activity, there's been a lot of technical work going on in the background, some of which is, a lot of it which I can't talk about in detail because the IP is protected, but the big, huge focus of the work, of course, is the new wing design. And maturing the wing design, the truss, the interface, and all of that was a really key part of the activities going on. But really, one of the biggest challenges of all is now you have a very thin wing, much shorter chord, much smaller volume to deal with. So that is really one of the key technology innovations is how do you get everything in that? Like the project manager at Boeing is, how do you get the stuff in there? It's actuators and wiring, and in our case, instrumentation as well, and fuel, and it's very complex. And now you have to integrate a high-low system into it. Eventually, they'll have to put a de-icing system in. You have to, even though we're not going to have that, you have to account for it for a production airplane. So the challenge of that is enormous. And if we had a drawing on the wall showing the difference sort of between today's single-aisle airplanes volume in the wing compared to this, you would be shocked at how much smaller the area is. And then you got to design it for long term, right? You have to design it to be maintained and inspected, and so you got to have access panels and all of that. So it's quite challenging. And parallel with all that, lots of good work between NASA and Boeing. We're sort of both doing computational fluid dynamics work, a lot of it partnering very well. NASA has engineers embedded in many of the Boeing IPTs, in addition to doing a lot of these facilities testing things I pointed out. So the team has really gelled well, and everybody's got the same goals. We're trying to get to a point where we can make basically a decision, Boeing can make a decision on whether this concept is the right concept for the next generation of airplanes. Other things going on is we're building up some ground test facilities. This is just a couple, there's many others. On the left there is the Boeing current MD-90, they call it the avionics systems bench. So that's being modified into the configuration that we'll use for the X66 and being used for testing and sort of hardware in the loop testing and software testing and so forth. We've already had pilots in there flying it, looking at handling qualities of some of the early Aero models. And then on the right, we're actually doing some other sustainable. We're doing some reusability, some reduce, reuse. We're reusing an MD-90 cockpit that we bought out of a boneyard. We're parting that out over at NASA Armstrong, and we're building a piloted sim there. So that'll be at the flight test location. I didn't mention that once the airplane's built, it's going to be flight tested for about a year at NASA Armstrong. And so we're going to build up a cockpit using all the parts from this to mimic what the what the X66 will look like. So that we really get good pilot training. We can do training for missions, planning for missions. We can do emergency procedures, training and checkouts. So I think it's going to be a very valuable tool for us to use going forward. Just a couple other quick comments. Boeing's been, it's a huge effort to pull an airplane like this together. They've got a ton of suppliers on their list, but when I talk about partners here on the left, what I'm talking about, these are companies that are contributing, not just participating as a supplier. So they're providing money or people or so forth. So they've really put together a great team to support this. We are using geared turbofan engines for the propulsion system. So RTX's and Pratt & Whitney, of course, is involved, and you can see the list there of other contributors. If I had the list of everybody contributing, there would be 100 companies listed there. And then the other thing I thought was really unique that Boeing did, they pulled together an airline sustainability coalition, which is a group to kind of advise this airplane development over time, to inform them of kind of how the progress is going, but also have airline feedback with their thoughts and concerns about the configuration. And so we're meeting with them several times a year. We actually have the next meeting next week. And I think that's all I have. So we're going to turn it over to Swati. Thanks.
Okay, so I'll go back to this side of the stage now. Hello everyone, thank you for joining us this afternoon. I'm Swati Saxena, and I'll be sharing some information about the work we are doing in aerospace operations to contribute to NASA's Sustainable Flight National Partnership SFNP mission. So I manage one of the projects that we have at NASA within our air traffic management portfolio. It's called Digital Information Platform, and what we are really doing is developing a cloud-based infrastructure. A cloud-based infrastructure to deploy digital aviation services and then successfully deploy them in the field and collect real-world data to showcase sustainability benefits such as reduction in fuel emissions, carbon emissions, and reducing the overall impact of the aviation on the climate. And the objective, really the high-level objective here is to make progress towards the FAA's Info-centric NAS initiative, their vision, and at the same time reduce climate impact due to aviation. So how we are doing this? So we have planned a series of field tests, flight demonstrations spanning across this decade, as you can see on this arc chart here, going from bottom to top, by deploying these digital services into the field, equipping the flight operators, our airline partners with these services, and then they are currently using them in their day-to-day operations. So starting with the first demonstration that's currently going on in North Texas region, Dallas-Fort Worth, TRACON area, focuses on reducing traffic congestion by suggesting alternate routes to flight operators and redirecting the traffic through the TRACON boundaries. So that's the pre-departure rerouting algorithm that NASA has developed. It's an AI machine learning based algorithm currently deployed live in the field. And it's an operator tool that allows them to look for alternate routes in case of a weather event, for example, and then submit their request to the ATC, air traffic control, for their approval. And once it gets approved, the aircraft reroutes to a different, more efficient route, not only reducing delays on the surface, but also reducing carbon emissions and fuel burn along the way. And although this tool is currently developed to modify the trajectory or path for a single flight, it has cascade effect, cascade benefits that you see across the entire traffic in that TRACON region, and then the fuel savings and the carbon emission savings also build up. Even when the aircraft is taxiing on the airway, it's spending fuel, it's burning fuel, it's emitting carbon. So when you are reducing any delay in getting the flight into the air, you're actually reducing, making savings, carbon emissions as well as fuel emissions along the way. So this is what we are doing currently. We will be expanding to Houston airspace next year with this pre-departure rerouting tool. And then we plan to build on this capability and expand it to post-departure integrated rerouting in our next demonstration, which will end in FY27. So that's the planning work that we have already started with our airline partners, and we are planning to expand our ecosystem, our partnership ecosystem, to bring other industry partners on board to make this integrated gate-to-gate trajectory management field demonstration. We'll be further building on that and moving from the single flight of trajectory optimization to fleet-wide impact by addressing some of the other challenges that are currently there in national aerospace systems, such as IROPS, intelligent disruption management recovery, and other problems and other use cases that impacts multiple flights at the same time. And then in near about the end of the decade, FY30, we plan to do a live demonstration by incorporating different technical capabilities we develop along the way, along with our partners, FAA and industry partners, third-party service partners, to do a 4D trajectory optimization demonstration. So I'll tell you a little bit more about the current tool that we have, capability that we have deployed in North Texas, and how it's showing the sustainability benefits. So as you can see on the picture on the bottom left, there is traffic due to a weather event. The traffic builds up, there is traffic congestion, and then which results into delay on the surface. So the algorithm that we have built so far redirects that traffic to an alternate route, relieving that congestion and reducing surface delays. So once there is a set of pre-approved routes, TOS, trajectory option sets, that operators have access to, and then they run this service to find an alternate available route and then submit it for approval. And once it's approved, you can the flight just takes the alternate route, which ends up in both fuel and carbon emission savings. So this is currently being used by our partner airlines, American Airlines and Southwest Airlines in the North Texas region, and we have United, Delta, and JetBlue now starting to adopt this tool as well. Their operators are getting trained, and we are seeing more and more real-world benefits from this service currently in North Texas region. And then, as I mentioned, we are expanding it to the Houston area next year, where we will start to collect more data from the field and have a better assessment of how the benefits would scale if we deploy something like this across the nation, across NAS. So in this operational demonstration, we have several partners and where we have to work in close collaboration. And since this is being used in the current environment, in the current aerospace operations, it has to be approved and safe to fly, to be used in the system. So FAA is a key collaborator and partner in this effort, and we work with different FAA facilities, the tower, TRACON, and the local ATC representatives to make sure they know how we are coming up with these solutions, how they are getting integrated into the system, how the request is being submitted and finally approved. So we have in the North Texas region, we have American Airlines, their operations center, so two major airlines hub, American and Southwest, within 50 miles of each other, which makes it a very complex environment. And we have our research outpost there, co-located within a FAA facility, North Texas Research Station, where we have this tool currently running live in operation 24/7. So we coordinate between different facilities, different FAA facilities, different airline operator facilities to deploy this tool and collect the live data from the field. So this year will be our third year for collecting this data from the field, and we have been capturing these benefits that we are realizing and then converting them to different metrics, so that it's easier to understand, it's easier to relate to the sustainability benefits that we are seeing in the field. So just in 2024 itself, an average reroute saves about 1,000 pounds of fuel, nearly 3,000 pounds of CO2, and which is kind of equivalent to planting 21 urban trees. So that's kind of our average estimate of how each of these reroutes saves. And this is not just across the fuel savings and emission savings, but it also has business implications for the airlines. So if we look at the numbers for passenger cost savings, nearly $4,000, crew cost savings, total off delay savings, which is basically the overall system savings that ends up happening because of these reroutes, and then the total in delay savings of nearly 6 hours as well. So this is what we have been, the type of data that we have been collecting. And if we look at the number of candidate flights that were eligible or that were identified by the solution just this year, it's close to 630. And out of those, around 109 requests were submitted, and then almost 50% of those were approved. So there are different reasons why there you see that gap, and we are trying to address that now. One of the reasons is to make the staff available to run this tool on the operator side, train more people on the airlines operator side so that they know how to use it. And then coordinate better coordination with the ATC facilities. Right now, some of this process is manual, some of the information that gets shared between airlines and on the FAA side is manual, so that's something that we are working on. If we can automate that process, have a user interface that directly submits that request for approval, that would close some of the gap that you see there. But over the last 3 years, as you can see, 2022 is when we first started to collect this information. We have been seeing continued benefits, and we are planning to build on this capability, include the post-departure rerouting as well, and then we'll be partnering with other industry partners, as I mentioned, to kind of make progress on the chart that I showed before for other operational demonstrations. So with that, I'll hand it over to the last speaker, Dane.
Hi, everyone. Am I on? There we go. So good afternoon. Thanks for sticking with us this afternoon. Oops. Hold on. There we go. All right. Sorry about that. So my name is Dale Van Zanti. I manage the Advanced Air Transport Technology Project, or AATT. I'm going to be presenting today. Eric Hendricks, unfortunately, couldn't travel this week, but he manages this part of the bigger project for the system analysis and integration, and that's where the model-based systems analysis and engineering workflow sits. So diving into that, you've seen this chart from a couple of other folks. We affectionately call it our swoosh chart. But down the left-hand side there, you see the different technology swim lanes that you've already heard about from the other presenters. As those technology swim lanes come to a conclusion out in the 26, 27, 28 timeframe, they'll have their results. From all of those separate technologies, it isn't either time or cost feasible to build a demonstrator that would combine all of those technologies. So how do we determine if we've met the SFNP goal? Well, we are building a model-based system analysis and engineering system where we'll combine all of those technologies into a digital flight test out in that FY29 timeframe, and that'll be our way of measuring if we've met that 30% fuel burn reduction target of SFNP. Now, these technologies that are on this chart are the technologies that NASA is focusing on, and each one of those swim lanes contains a major either flight test or ground demonstration, but SFNP is a national partnership, and we have other partners like the FAA who are also maturing technologies that would be applicable in the 2030s timeframe. So one example that sits within my project is we're collaborating with them on the GE Open Fan. So it's an FAA Clean 3 sponsored project. We're doing the wind tunnel testing at NASA Glenn. So we'll have the performance and acoustics for that propulsor concept, and that becomes part of that broader national partnership technology mix towards that 30% fuel burn reduction goal. So another way of saying this in words instead of graphically is, we're building this system-level digital integration framework across for now, the SFNP technologies and projects. And that's going to support the assessment, the advancement, and hopefully the adoption of these sustainable technologies for the 2030s as they go into service in the subsonic transport market. Down there in the lower right, you see that MBSA&E kind of sits at the center with these other projects and technology swim lanes around the outside, feeding in information to that analysis system, and that's how we'll get an estimate of our success. On the left there, you see the objectives for the task. A couple important terms there. It's an open framework, we intend to be able to give this out, to share it with industry and academia, and actually to have them be able to contribute models and be in collaboration with us continuing to build the capability. It goes across projects, it goes across programs at NASA. Some of the components of the framework are coming from the TACP project, the Transformative Aeronautical Concepts project, and the T-Cubed project specifically within there. External capable, meaning that we'd like to be able to collaborate with, airframe or engine OEMs, for instance, and get access to their proprietary, potentially, models, into the broader framework. We're still figuring out how to do that. And then once the framework is in place, that's phase one of the work, then we want to conduct these coordinated integrated systems analysis studies of the current set of technologies, but then going forward as we look at new concept airplanes with new technologies to continue to build out the framework and use it. Part of this is coming up with what Eric calls a digital hangar, which is a set of airframe and engine models that are common, open, reference, and they'll be usable by anyone in the system. And in that way, we're starting from sort of validated or vetted models for engines and airframes where you can launch off and do an analysis and be assured that you should get the same answer. And if you don't get the same answer, it's not because you're using a different engine model than we were. There's something else going on in the assumptions. So as I said, we're doing this in actually two phases. We're currently just finishing up phase one, which is actually to get the initial framework in place. Across the center there, you see some of our external partners for which we have contracts, Boeing, M4, Georgia Tech, and Northrop Grumman. At NASA, we don't build airplanes or engines. So bringing in these outside partners is very helpful in making us sure that we have the interfaces correct between all of these different components that go into the framework. Next year, we'll be actually moving into phase two, which is more application of the framework. It's not that we're necessarily done building components of it. We'll continue to add components as needed as new technologies come into the aircraft systems. And then as Rich alluded to, we have the ACES 2050 contracts, which are so close to being able to, very close to being able to tell you who they are, but not quite yet. But that's looking at the 2040s and 2050s aircraft and engine systems. We're expecting to see changes in energy source or more electrification, other technologies that we'll have to model and add to the framework going forward. So it is meant to be extensible, adaptable, flexible. So this is a high-level view of what this whole framework looks like. In the upper left corner there is the actual system engineering piece of it, implemented through Magic Draw. That's where some of the requirements sit, the overall system sits. On the right-hand side is the model-based system analysis portion, which is being implemented using Open MDAO. That allows us to link together a whole series of disciplinary models. I'll show you what those are next. But it's an open framework, and it also allows us to wrap an optimizer around those models. The MBSA and MBSE are linked together with that driver sort of down there in the lower left corner that does the communication between those two different aspects. That also allows us to add uncertainty quantification to these kinds of analyses. So what models are in there? So kind of that pie on the right-hand side shows what all the disciplines are that are currently in the model. Now that doesn't mean that we're limited to those. We could actually add another pie slice for a different discipline if we need to in the future. So you see there's a range of different disciplines from aerodynamics to noise to a cost model. And within each one of those pie sections, there's a range of levels of fidelity, from low order one-dimensional tools out to higher order tools. For instance, in the aerodynamics there, you see Fun 3D listed in a little cloud, meaning that it's still in the process of getting it implemented into the system. But you have the ability to choose the level of fidelity that you want to use for the analysis. And for some of these newer systems that are highly coupled, it's possible that we'll actually have to start with the higher fidelity tools first to kind of get us in the right ballpark for that. Around kind of the center there, you see aviary listed, so that's a newer version of our flight optimization tool. That was one of the big partnerships with T-Cubed, and a large contribution to the overall framework. So we have done some demonstration problems with the framework. This is one of them, a TTBW with a hybrid engine. Now this is not Brent's X66. This is actually a non-proprietary NASA tech collector for the TTBW. It allows us to go out and look at different future technology studies on an open system. It does use the GFAN Plus hybridized engine. This was originally intended for a mid-2030s entry into service. So this allowed us to kind of stress test the system, compare the results that we're getting from the new framework to the legacy tools. The legacy tools were typically run sort of in standalone mode. This morning, a speaker was talking about silos. The framework is meant to break down those silos and allow a truly optimum system across multiple disciplines at once. We've run a series of other tests with the system here. In the upper left there's some parametric or sanity checks, from the new framework back to the legacy tools. Are we getting the correct trends? Are we getting what we expect? Yes, we are. It's operating well. In the upper right-hand side there, we did an aerostructural optimization with the TTBW wing. So it was optimizing both for structure and aerodynamic efficiency, and then would loop back around and change the propulsion model as the weight and thrust requirements change. So you get a truly multidisciplinary optimum from linking everything together. Then on the bottom there, you see two papers that were actually presented here at the conference, a hybrid electric propulsor optimization, and the MBSA&E uncertainty quantification work that was done. So with that, I think that's my last slide. I get to turn things back over to Rich.
All right. Thanks, Dale.
Need that?
Yeah, I'm sure we're going to need slides, but so we're starting to get a number of questions coming in. I guess the first thing I want to say is I really feel honored and privileged to be working with this team, their teams that they represent that are in NASA, in industry, in other government, and academia. It's really a very broad, large team, and I can't believe how much we're accomplishing and where we're heading. I'm reading the questions here. There's one question that's racing up the board quick. I'm going to save that, but I'll ask it, so don't get worried. There's a question that I'll take first that says, has sustainability succeeded in helping NASA aeronautics justify a greater portion of the NASA budget? And so what I would say is historically I've seen us in the 3 to 4% range of NASA's overall budget, and honestly I think we're still in that range, kind of trending closer to 4 maybe now. But it's not like we've seen a jump. But what I will say, a big jump to like 5 or 6 or something like that. NASA has a lot of great missions, the space mission, science mission, and aeronautics. And budgets are challenging every year, but overall the trend has been up for the last decade, a few down years, but we're trending up. I think sustainability helps because people realize that it's a extremely important challenge, and it's not just the environment, but it's jobs. It's there's a lot of good reasons for it. So we tend to have support. And one thing that's, I think, a really good sign is that for the first time ever, beginning last June, there's a Congressional Sustainable Aviation Caucus. And so there's a bipartisan group that gets together to learn more and be active in sustainable aviation. So that's extremely positive, I think. Partners, there was a question here on partners. Partnerships throughout all this you've seen are important. And the question was about NASA has proven our ability to successfully partner with industry. How does industry competition impede your efforts? And I'll add to that, maybe if it doesn't impede efforts, does it enhance your efforts? Any one of you can take that, kind of talk about partnerships and competition.
You're looking at me for.
So maybe I can.
Go ahead.
chime in because this is something. This question is something that we have been asked before, and since we are doing live field demonstrations, we have our capabilities right now running in the field. I sometimes get asked if we are competing with the industry. We have a platform that hosts these digital services that are being used in the field and collecting live data. So our answer is, I think, which you mentioned. We are not competing, and there is with the industry. We actually want to enhance and kind of bring the industry together to build on what we are doing. And an important aspect of the work that we do here is tech transfer and how we want to make sure the technical capabilities that we are developing through our research and work gets transferred to other agencies like FAA in our case, as well as industry. And one other example that I'd like to mention here is to demonstrate the fact that we are, it's not the competitive nature that we are kind of working within. We are working on demonstrating the concept of platform interoperability or services where we have a platform that NASA is developing, and there are other platforms developed by third-party vendors or other members of the industry, and how we can demonstrate the concept of platform interoperability and set up requirements so that we can build this ecosystem of digital services that are going to be available for not only the current fleet, but the future operations as well, which will include integration of different types of aircrafts, even extending to autonomous vehicles and urban air mobility.
So maybe I'm going to switch it around from the impede. Several of you have gone through competitions, phase 1s to phase 2s. How would you say that has helped you get better products or better phase 2s?
I think it does help. I know that the nice thing about doing phase 1, you can get to a point where you see how the technologies are developing. Some may be going better than others before you start considering them for a second phase. And back to the competition too, I think there are pluses and minuses. I think the competition is good because you get better proposals and better quality because there is a competition. There's no guarantee. And I do like the fact that we're doing these cost shares because for industry to actually have some skin in the game when we're sharing the cost, it doesn't ensure, but it definitely increases the probability that these technologies are actually going to make it into the fleet, which I think is really important. But the downsides are when you're going to TRL 6, you're not going to be able to reveal the secret sauce of every technology, right? So there's certain things we can reveal publicly, but not everything. So there's definitely pluses and minuses to it. But in this case, I think where we're headed with a new potential aircraft, I think the pluses outweigh the minuses.
Yeah, just piggyback on what was just mentioned. I think it's important to note just how much money the companies are putting into these. So it's not just NASA dollars that are funding these. Brent brought it up, the dollar value that Boeing's putting into X-66. So they definitely have the right to protect the intellectual property that they're developing there. And then I think we have the opportunity to work together and find out ways where we do have common interests where we can collaborate. So we had some discussions with a number of different companies that we worked with on the EPFD project yesterday afternoon. And there was a good discussion about what we might be able to do on the regulations and standards front so that we have common means of compliance for how these new technologies are going to be certified, what kind of engagements need to happen with the FAA. Another key part that I didn't mention in the presentation, but the EPFD project also works with a number of academic institutions. So we have a larger partnership with Georgia Tech and also a partnership with the University of Michigan. And in my experience, one of the things that has been very beneficial out of those partnerships is that we're able to develop a generic model. It doesn't have to be a perfect model or something that will definitely be something that flies in the future, but having that generic model that then we can go test various technologies against and the companies feel more engaging on that front, it allows us to have opportunities to see how those technologies provide those overall benefits on those future concept studies.
Okay, thanks.
I wanted to comment a bit about our experience in collaboration. We've been pretty successful in our activity to pull together people who have been competitors in the past and have just historically been protective, living in a shell almost in some cases and being suppliers to others but not really working together. And for what we're trying to do now, I think people realize that they're trying to do something pretty grand in a short period of time, and really in order to be internationally competitive, they really need to work together and take advantage of each other's expertise and leverage each other's resources in order to move the technologies ahead faster. I think we do have, in some cases, competition that it's not a competition before we make an award, it's competition during execution. In the sense of by being on a team where you pick sort of a common, less sensitive geometry and problem to work, we are basically getting people to observe each other's behavior, and learn from that, and then in doing so, basically accelerate the development of their own technology. We also realize, I think we just realized recently that if we're successful at launching this next airplane and building as many airplanes as being envisioned, it will require the entire manufacturing base and multiple providers, not just a single company. So I don't think they're viewing this as a competition to see who wins. It's going to be multiple winners contributing to the production of the next system.
All right. While you've got the mic, Rick, there's a popular question for you. Can structural technologies developed in HICAM be applied to other vehicle types such as truss brace wings or electric aircraft? And I would extend that, any other vehicle classes.
I think the answer is generally it's beneficial, and I would say generally yes, but I would also say not directly. In the sense of what we find and what we're doing now is that there's lots of variables and knobs to be turned in designing a production system, and you really have to look at the application in order to select the best materials and processing forms in order to optimize toward that construct. So I think we're doing, in some cases, a sort of a point design. We've got lots of different areas on the aircraft, so we have multiple point designs when it comes to the best production system for this class of part or this class. So I think we're developing technologies that are tailored specifically toward this vehicle. That being said, the translation of those technologies to different forms. I think the geometry, for example, for truss-braced wing is different, but it's envisioned that the approach for structural configurations of stringer stiffened panels and construction will be very similar. Modified, but similar, with some very unique challenges associated with some of the complex joints. So I think it's generally applicable. When you get into something like an urban air mobility, I think you were envisioning much lighter gauge, much higher production rates, so there would have to be tailoring of what we're learning to those specific scales.
Yeah, okay.
So I'd say I would say many of our people that are performing this are doing so because they do realize that advancing in this area will enable them to do better in those areas also.
Learning is applicable more broadly.
That's correct.
We have a pretty particular focus. Joe, it's understood EPFD is a tech demo, but what are the benefits of hybridizing regional airliners with battery mass, less range, et cetera?
Yes. So electrification definitely has some challenges on the energy storage front. The benefits that you're really getting on the electrification is the increased efficiency of the electrical powertrain in comparison to the turbo machinery, but we're not going to be a one-for-one transition if the energy storage is an order of magnitude energy density difference with Jet A. The efficiency benefit with the electrical powertrain does mean that we don't have to be exactly one-for-one with Jet A, but there will be challenges, and we're going to have to try to address those. One of the things that we've been able to take a look at on the regional side with Magni-X, their Dash 7 is the vision vehicle that they're trying to go be a commercial product in the mid-2030s. Ben Loxton was here and gave a couple of different presentations throughout the week, and they're looking at really large benefits on the 100 to 200 nautical mile missions and still providing around a 10% benefit on the regional side with a 500 nautical mile mission. They're targeting to get to a 450 watt-hour per kilogram battery to achieve some of these, but just to be a minimally viable commercial product moving into the next generation, 250 watt-hours is what they were looking for, so that is definitely in the realm of feasibility for the next generations for some of these regional concepts. With the shorter range, due to the battery technology there, it may be that some of the first introductions are a little bit smaller niche markets in terms of shorter hops and trying to rejuvenate some of the regional airports. But if we are successful and they're able to actually get a regional hybrid electric aircraft flight certified, I think that opens up the space for us tremendously. Once we have that sort of certification process laid out, the means of compliance for doing these hybrid test flights, I think that would be a very significant accomplishment. And the transportation sector in general, I think, is electrifying, not just aviation. So there's a large push to get to better batteries. So NASA's doing some work in batteries on the aviation side, but we really need to leverage the Department of Energy's work and some of the other work that's going on throughout the industry. So we're trying to follow closely the work that's being done by ARPA-E, and then also working with the DOE to make sure that our grid gets cleaner in time as well, so the electrification really does provide that net zero emissions benefit.
Do you feel the demonstrations in the turboprop class are effectively teaching us how to scale up to airliner?
I think so. I think that will definitely get us on.
Tony needs it.
Yeah, we definitely have a process in terms of where we would like to see the technology go on the battery side. I think battery introduction on the regional prop in the very next generation is a huge step forward. When Christine Andrews was talking about some of the GE concepts and some of our internal studies on the larger single-aisle aircraft where we may have a bigger impact on the aviation market in general, we're really looking at using electrification without having large energy storage. So we're looking at those mild hybrid concepts where we're still getting a net benefit with the electrification, but not really relying on the battery as a primary driver for propulsion.
Okay, great. You mentioned the Department of Energy, so I'm going to take the second highest question on here now is, should challenges related to SAF production and uptake be included as part of NASA's portfolio of projects? And I bet none of you want to answer that. So I think, we've thought about that in the past. There was a decision that within NASA's budget, which is a very nice budget, there are other agencies like DOE and the FAA and USDA that are chartered more specifically at that. And so we might have a few efforts, small seedling kind of efforts that look at that to try to seed those other efforts. But unless we had a significant increase in budget, it kind of doesn't make sense for us to focus on that and to leverage and work with other agencies. So that's the tack we've taken. We have a role where we assess the emissions of different SAFs, for example, but we're trying to stay out of the the production of it per se. Dale, how is MBSAE different or complementary to Boeing's Cascade tool? And I would extend that to things like Cambridge's AIA and other kind of tools like that.
Okay, so the Cascade or Cambridge's Aviation Impact Accelerator, those are sort of like weld-awake, fleet-level kinds of assessments of climate impact. What we're using MBSA&E for is really trying to tie all of our analysis tools together, into a coherent framework, and then allow an optimizer loop to go around that. So it's aimed at analysis of the vehicle performance, and not at the moment, expanding out to looking at like these fleet level models. And it's also, a lot of these performance estimates are time consuming, and we used to email engine decks back and forth to each other and all those kinds of things. So having this framework where everything talks to each other, and you have the systems engineering, the version tracking, the verified models, the verified airframes, will help increase not only the speed of the analysis, but also the traceability and hopefully the accuracy of that. But it's kind of doing two different things.
Yeah. Brent, we're going to go to you. This is a question about the $425 million that's NASA spending on Boeing, but we also have other internal efforts. About how much more are we spending there compared to the $725 that the Boeing?
Yeah, we haven't ever announced that publicly, but it's a sizable amount. Right now we're at about 50 people, and we will ramp up to roughly 100 people during the peak. But we're also supporting, as I mentioned, these wind tunnel testing. Those are expensive tests to do. They're also going to be using the facilities at Armstrong for more than a year to do all of the flight tests. That's a key thing. We have some loads lab testing of some of the structural components. We'll be helping with some fabrication of things like instrumentation and instrumentation installs. I mentioned the simulation. So when you add all of that up, it's a pretty sizable investment on our part over 7-year effort. I can say that when we did the proposal evaluations, each of the proposers could decide, put in their proposal, do you want any help from NASA or not? We didn't actually judge that at all. It wasn't a criteria. So there were several companies that said, we got it, we can do it, just send us money when we achieve the milestones. And that was fine. So when somebody put in a proposal that said, hey, we'd like some help, we actually costed that out, added it to whatever they were asking from NASA, and that's what was judged by the selection official. So it was balanced across that and was taken into account. So now going forward, we know what that dollar number is, and as we make changes to support different tests or put more emphasis on some work, less on another, we make sure that we stay within that original commitment dollar value over the 7 years.
Yeah, so the other part of that question is those NASA researchers that are working on that, are they able to share their publicly funded results? And I think they're going to be bound. There's going to be publishing, but limited publishing.
The Funded Space Acts, by law, provide a significant amount of IP protection to the partner that's putting in significant amounts of money. There are some government use rights that we can do with certain things. And of course, we do research with our partners. All we have to do is say, hey, this is what we'd like to publish. They review it and decide whether that's acceptable or not. We take the lead from them on whether or not something is considered proprietary or not. We have a lot of protections built into the program to protect the IP, but we get what we need to do the work we do. And some of the data that we'll collect and the models we'll validate will feed some of what Dale was talking about in terms of the model-based system engineering. It's a great database to help validate models, but it won't be done in a way where the models can now exactly predict what this vehicle is going to do. It's done in a way that the models accurately predict whatever they're going after. So it's a database that we're not handing it outside this, but we're using it to improve our tools.
So I'm going to extend over to Dale because the truss brace wing work kind of began in his project a while ago, and there's still work going on. But there's different sets of rights, different publishing. There's still some restrictions, but you might kind of expand on, speak to what we're doing, what AATT is doing in
for truss brace wing. So within AATT, we do still have truss brace wing work. We are doing the technology maturation work. We're looking at some of the what I'd call risk reduction for corners of the design space kind of thing. We're also looking at other things like doing a noise estimate for that aircraft configuration. We're looking at icing. Are there any, because of the configuration is different, are there any showstoppers out there for these kind of like off nominal conditions? So that's where AATT sits, and it's different but complementary to what Brent is doing with the flight demonstrator.
And you're not really focused on the X66 demo vehicle. You're looking at concept vehicle.
We're actually looking at the vision vehicle. If it becomes a product, we're trying to do estimates of how would that vision vehicle perform in terms of fuel burn, noise, emissions. So it's different than the X66.
Yeah. Swati, so it was extremely fascinating when I visited North Texas and saw all the tools in place. And, I asked, how does it transition? And what are you going to do when the demo ends? And they never wanted it to end because they're so enjoying the benefits of the technology. But so it's in Texas now. How long does it take for a technology like that in air traffic to become ingrained in the national airspace around the country? How does that work?
Yeah, absolutely. So we started with North Texas, and as I mentioned, we have some machine learning models built into the technology, which are trained for that airspace. We have already started to expand those to Houston, as I mentioned, and then to other TRACONs as well. Currently, we are looking at deploying these capabilities into New York airspace. We've already started to look into other complex metroplex areas such as Chicago, Florida region, and so on. So since we have deployed this technology onto the cloud, it's really not tied to any physical hardware anymore. So even today, any operator sitting in any location across NAS can log into our cloud-based platform and get access to the service. So that capability is available right now. We are just in the process of training the model to different airspaces, and also we are looking into doing a NAS-wide, system-wide benefits assessment. So we know we get an estimate, we can tell operators, we can build that case that if this is available across NES, we can be looking at tapping into a lot more savings, a lot more potential to contribute to sustainability benefits.
All right, thank you. All right, so we're down to like the last 3 or 4 or 5 minutes, and so I'm going to go to the top ranked question that's been asked, and I'm going to read it as it's written, but then I'll tweak it a little for you, and each one of you is going to get to answer this. This is a great portfolio of efforts. If you were appropriated another $200 million per year, what would you prioritize to add? And so we're not going to sit up here and give you a prioritized list, but I'm going to let you be creative a little bit, and based on what you know. I'm sure each of you has a different answer, but if you had the opportunity to do more, what would it be? Dale.
Oh, wow, yeah, that's a hard question. So I guess, one thing that maybe we haven't talked a lot about today is non-CO2 and contrails and building out that information, because that answer is going to drive a lot of the technology going forward. If hydrogen is never going to be a good thing to do for that standpoint, we need to know that answer sooner rather than later, because there's a lot of effort at OEMs, doing a parallel technology path right now, and getting to that answer soon would be good.
I'm going to go down the line. Swati?
Yeah, so this was, I was going to say non-CO2 impact as well, and that's, and one area on the operational side of things related to contrails is we need a lot of data. We need real, flight data, not single flight tests. We need, multiple flights over a period of time. So some of that money can definitely be used to collect the data that's really required to develop that confidence in the models and have a solution that's applicable in the current operational environment. In addition to that, the other area where we can really invest more is how we integrate different vehicles. As I was mentioned before, there is another initiative we have in air traffic management called Sky for All, which is looking at more how the future skies would look like. So that could also use a lot more resources and investment.
Brent.
I'd say, if we had the money available when we awarded this, we really would have loved to have awarded more than one. Most funded space acts award multiple because you're trying to achieve some, like Commercial Crew is a good example, right? We've got now multiple paths to take astronauts to the space station. And so that's a good use for a funded space act. So it would have been nice to have awarded a second one. There were definitely other great concepts there. Today, if they handed me money, I'd say go faster. I mean, we have we all feel this urgency to transform, and you can't transform it overnight. It takes a long time to build these airplanes, to replace them into the fleet, and when we have this 2050 goal, there's a timeline there, and money would really help accelerate things right now, I think. It is one of the key things that's pacing what we're doing right now.
Yeah.
If we had a little bit more, we would definitely accelerate.
Yeah. Rick?
I have probably 3 different directions. I don't know how I would prioritize that. First,
Number one.
I'm going to tell you all 3 because I might get more money that way. So I guess the one thing we would do would probably go to a larger size on our components would definitely reduce risk. That would be one thing, one approach, and that would be the easiest thing to do. The next thing that would be of interest would be expanding the scope, in the sense that we picked a very subset of the problems because that we thought were the most important and the hardest to do, but it's easy to identify a component right next to it or an application. Again, we've talked about out on the engine structure, and there's lots of other parts on the airplane that where composite structure could benefit and ultimately benefit the aircraft. And so we could expand the scope of application on that. The third one actually goes a step further, saying, what about, again, goes to your question about what about another platform? Mm-hmm. What about a future vehicle? And I think then there's interest in high rate production for urban air mobility applications. They're not quite there yet, but that's an emerging. And if we had some funding at this point in time, starting to think of thoughts of developments in those areas would probably be a good place to start.
Okay. Tony took a sip, so he's ready.
I'm ready. The first two things that come to mind would be, after the core demo, do a full engine, put a fan on it and that, but I wouldn't do that. The other option is do a second core demo, right, if you could award it, and I wouldn't do that either. Okay. I think...
He's been thinking about this.
I had some time. So I think we got to look beyond SFNP when it comes to the engine, right? So we're doing what we need to do now. It's going to run on SAF. It's going to be efficient, but we can push the turbofan engine more.
Yeah.
High-tech's great, but we can still push it more. There's a lot more to do there. Run on other fuels, make it even more efficient, bring in the hybrid electric element even more. So start whatever the next follow on the high-tech is, instead of waiting till it's over. If I had another 20, 30, 40 million to work with, I would start the next project right now in parallel with it for what's after.
All right. You get the final word.
Yeah, final word. I mean, it's an exciting time at NASA with all these different demonstrations going on. It's a unique opportunity, I think, to see all these, because it's not every day you get to do a drawing board concept and then do component testing and then be able to justify to leadership that it's ready for a real scale demo. In the electrification space, there's a lot of new players, so having a new company join the demonstration space would be nice. But I think the priority for me would be we have a whole series of great demonstrators right now and in partnership with industry. I would like to be able to leverage all of the learnings that our workforce is getting through those partnerships and see more of a larger scale demonstration with the NASA workforce and a NASA concept. So then we might be able to do more of that public direct dissemination that was mentioned in one of the earlier questions.
All right. I think that's a good set of answers. So with that, I think we've reached the end of our time. So I want to thank the panelists and thank all of you for joining us here today. And let's give a round of applause to the panelists again. Thank you very much.